some more studying in on electrodynamics and quantum, seeing if there's anybody around who's interested in learning some electrodynamics. Anybody have any questions? I left my pen over there. Let me get my pen. So I'll just be working through some problems, see if anybody show up, and we have a lot of problems to go, so they continue into tomorrow. I did do a sort of preliminary, you can see, assessment of the mass and rotation distribution in Persepi. So I may actually do that, present that Saturday at my regular time and get some feedback on it. So I'll be doing that presentation as an assignment on uh, Tuesday. So, and I'll probably do some more quantum or electrodynamics then. So looking at this problem here, we're looking at the hollow cylinder radius r is uniformly charged, surface density sigma. We're going to use Gauss's law to determine the electric field at these 2 points. Is one of the things that MC Toon pointed out. The flat earthers and other globe deniers and their ignorance and stupidity, they mistakenly believed that a Gaussian surface was an actual thing. Trying to, how they pretend like they know science and just learn a few buzzwords or whatever. But the Gaussian surface is this imaginary surface here at this location that we're going to use to get the electric field there. So I'll do that for these 2 points, and if I can't remember how to do it, I'll just look up the solution. So it should be uh, EDA cosine theta equals sigma A over epsilon naught. And the normal should be outward from the surface here. And the thing is, there's no charge inside. So there should be 0 for the inner part. There's no charge enclosed. There's a hollow cylinder with only a surface charge. So going to the outer one, about the same thing, but it'll be dA cosine theta equals sigma A over epsilon naught. The normal will instead be here, and the area here would be uh, the area of the Gaussian surface. So this would be E pi r2 squared cosine of 0, and this is sigma pi r squared over epsilon naught. So this should be E equals sigma r squared over r squared 2 epsilon naught. So let's look this up and see if I got this correct. All right, so the first one is 0. There's no charge enclosed. And the second one, got the area wrong. The area of a circle. It's 2 pi r 2, 2 pi r. So I forgot that we basically taken this cylinder here, and we have a cylinder, and I was to cut that cylinder and spread it out. this, like a flat plane, and the the arc length here would be 2 pi r, and the length you can say is L, the length of the thing. So the area is the length times the side, so it's 2 pi r2 L and 2 pi RL. The 2 pi and the L's will cancel, so we're left with sigma R2 over epsilon naught 2, or sigma R over R2 epsilon naught. That'll be the electric field at part 2 for R greater than R. And this is for R less than R. Right? That's easy enough. Uh, 316 says two concentric aspherical shells, radii A and B greater than A, have a uniform charge density. What is the electric field in between them? And how does the electric field change if the outer shell is charged? So now we have, imagine these are spheres. And we have A here and B there. And we have welcome to join. Be sure to drop a line. Let me know if you have any questions about anything. And we got A and B. So this one is charged Q positive, and this one is charged Q negative. And we want the electric field in between these. That's easy enough. Be the same as before. Uh, this law of the flux, the electric flux is going to equal the integral of the electric field dot product with the area. It's going to equal the charge enclosed over epsilon naught. And if I Gaussian surface here, all that R, you can say E dA cosine theta equals, and this is a thin concentric shell, so this would be sigma A over epsilon naught, and the area of this thing will be the area of a sphere. Surface area of a sphere. I don't think I remember it. You know, the uh, area of a circle. Look it up. What's going on, Sergio? How you doing, man? Been all right? Good to see you. Not remembering the surface area of a sphere. I need to remember how to integrate it so I could just integrate the thing. But I could just look it up real fast. Thanks for dropping the line, by the way. I should just remind myself how to integrate the thing. There's full pi. I was thinking of actually taking a line and integrating the line, but wasn't remembering exactly how to do that. But I mean, not really necessary. I could just remember surface area sphere is going to be 4 pi r squared. So that means that the electric field at the blue radius r, that'll be E 4 pi r squared. The normal at that point is coming straight out. So that's going to be cosine of 0 is 1. And that's going to equal sigma 4 pi a squared is where the charge ends over epsilon naught. And I'll check under a bit and see if I got this right. So this should be sigma a squared over epsilon naught r squared. Let me see if I got this correct. Like I got it correct, except for the solution didn't break this up into area. It just kept it as Q. I'm not sure, I'm not sure why. I see they were illustrating the fact that this is the same as if we had a point charge at the origin. So in other words, if I keep this, so this is correct, but as an illustration, let's say that I kept that as Q. So this would be E 4 pi r squared equals Q over epsilon naught. In other words, I kept the uh, Q, I kept the charge as just a charge instead of the surface density times the area. When I divide this, the electric field is Q over 4 pi r squared epsilon naught. Now, this K equals 1 over 4 pi epsilon naught. Like that's the definition of the K constant. It's one of the ways you can break it up. So this is Q, KQ over R squared. And this is actually the definition of an electric field equals KQ over R squared. So the solution is just showing the fact that the derivative of a spherical charge equates to having a point charge. It gives you the same, and of course that's where they got the brief definition from, I'm sure, since charges radiate spherically in all directions. So a point charge is, you could say, is an infinitely small sphere. Interesting thing I learned about in my quantum class recently is the electron. The understanding is that it's literally like a point. Like we know we can look at it as a wave, but if you look at it as a particle type object, it doesn't really have any dimensions. So the spin that an electron has is not really rotating. It's just a property of the electron. Like there's not a positive spin one direction and a negative spin in the other direction. There's an up and down spin, but it's more a property of the electron rather than the physical manifestation because technically it just has a point. It doesn't have any dimensions to even have a spin, like how a ball can spin. That's pretty interesting. So that's that. And it says, how would the electric field change if the outer shell is discharged? Since the outer shell doesn't have anything to do with the electric field, since there's no charge enclosed, it shouldn't change at all. Um, I do know if we have uh, plates, it adds together, but that's different from a sphere because they're literally an outside and an inside. The plate, both sides are technically outside, so I think that's what the difference is. So that's that. Yep, and the solution confirms it's independent of the charge of the outer shell. Let's say outer shell is irrelevant. About the charge enclosed in the Gaussian surface. And is that the last problem? It is the last problem in this one. All right, well, that's good. So give me a moment and I'll go ahead and swap over to the next homework. I don't think I added that one in here yet. So those who are watching How to Draw and Enjoy, anybody do anything on Thanksgiving? I don't really do much. I actually work a little bit at my security job. I just studied pretty much all I did. Go to homework three. I believe homework three is next. See what these have in store. Get through like two or three of these problems, maybe three. I'll try to do 23, 22, 23, and 25. I remember what these are, by the way. That's just why I'm running through them. I think I have these set 22, 23, and 25. I'll go through these and perhaps take a break. Share my pad again. These get a bit more complicated. Let me move some of these down. One more I need to get, but I have the 25 one. Here's these. So 22. Use the integral 3.32 to determine the potential both inside and outside a uniformly charged spherical surface with total charge Q and radius R. So let me find the integral 3.32. This is in the book Pollock and Stump. Integral 3.32. All right, so is this integral here? Potential, the electric potential equals 1 over 4 pi epsilon naught integral the density d3 over x minus x prime is the electric potential. Saying use the integral to determine the electric potential both inside and outside a uniform charged spherical surface. Total charge Q and radius R. I remember this one. Let me look at the solution. To my thought we would use there's a sort of formula that you can utilize. We won't be utilizing that. So what we'll do is utilize spherical symmetry. We want to determine the potential inside and outside. So this is our sphere. Um, you can say that this center this. You can say this is radius R. I should just say R. And within the sphere, we have a radius at that point going to the center. We'll call this R. Uh, we can label this the z-axis. And this would be the origin. So we're looking at it sideways, so the X and Y looks the same, is in the same direction. Um, so sigma, what is the uh, charge density, you can say, actually, if we do charge enclosed, it's going to be sigma times area, and the area is a sphere, so there's going to be sigma uh, 4 pi r squared, since that's the area of the sphere. And so then we can say that sigma equals q enclosed divided by 4 pi r squared. So that's our charge density. Um, Looks like we can actually plug this into this equation here. So x will be consistent with z. This is z. So basically um, the vertical height from the center of the shell. Um, and we can say that we want the potential both inside and outside. Um, so it's saying that this is z minus r cosine theta. So I'll make this theta right here. Our cosine theta is here, and this distance above that will be z minus r cosine theta. So whatever if I pick the point here, for instance, that's z, then I minus this distance here, r cosine theta, and then I end up with the distance here above that point. So this is the magnitude of this distance. So it seems like that's where they're going with that. So let's figure out what the magnitude of that is. We have the magnitude of x prime, saying this is the square root of z minus r cosine theta squared plus r squared. And the interesting thing is, as an aside, if we have a two vectors, so one vector here and one vector there, and if I called, I wanted to get the distance between these, we can say that this is x minus x prime. So we call one of these x and one of these x prime. That's the distance between them. And if I was to illustrate that, let's take x and I take x prime, but I swap it around. So basically, it'd be like taking this x prime here, but going in the opposite direction. You see how it's right on top of x prime, but it's going in the opposite direction. So this is still x. This now is minus x prime. And if I add these together, actually I could just copy this over. We see that the same thing fits. So that line is always going to be x minus x prime. So this x minus x prime will be a distance between 2 points. And what they're saying is that the distance would be here, which would be z minus r cosine theta, and here, which would be r. And so therefore I'm getting this distance from the edge to there. So it's becoming more clear why we're doing this. Because if I have, let me extend this line, I have a sphere, there's surface charge all the way around the sphere. So let's say I want to find out the potential from just this point here, from just this point. If I want the potential from this particular spot on the sphere, then the radius from that spot will be like so. Let's say if I wanted the potential here from that point there, the radius between these two will be the magnitude of this. So if I call this x, and I mixed up which one is minus or plus, but in the end it doesn't matter. But I'll try to keep it so that the illustration works. So this will be x, and this will be x prime. So the magnitude of x minus x prime would be the magnitude of z minus r cosine theta plus r squared. And that's why we can replace that. So taking this same equation, and I'll just copy it down. Copy this without making that. Saying that this equals, and this is K, so I'll just call it K. The book always wants to break it into parts. Maybe there'll be a reason later. So we have that. The charge density is sigma. I'll work that one out later. So we know we have this magnitude that I'm going to replace with z minus r cosine theta squared plus r squared. That's the magnitude of that distance here from some random point on the sphere to outside the sphere to get the potential there. Um, we have sigma, put sigma there, and 2 pi r r. basically we can say that this is dV, the volume. So I guess technically the area, 'cause that's a surface charge, this would be dA. So now we're looking at how we can best get the area at that point. So basically at that point, the area will be this area around here, like a little bitty area. So we can say the area is going to be, if I take a slice at that point, like basically this is like a slice out of the sphere. We have the length of the sphere, which is 2 pi and r. 2 pi r. This right here was r straight across. And then we have the height of this thing. Now this like they call the height r. They call in the fact that this height right here is r high. It seems like that should be different. Ending up with equal a integral sigma 2 pi r. And like we're only doing the top half. So if I was to add up, so basically this is at that particular ring and at this level, but I can add up the entire vertical component, which goes from 0 to pi. So then I can also say d theta to add up all of those, and this would be from 0 to pi. And I can just copy over my denominator, z minus r cosine theta plus r squared. Both of those are squared. So this theta and that theta is the same thing. This theta goes up and down vertically here, and that theta just goes up and down vertically between the whole thing to count up all of those. So let me know if y'all have any questions. See, there's one watching. If something is unclear as I work through this. So this is what we're looking at right here. We have the sigma, which is the charge density of the sphere. We have area, slice of the area there. Slice at a certain point. Then we add up all the slices. That, and then we do using the formula that they gave us. We take the radius from the surface to a certain point, the magnitude of that radius to P. Adding up all the light systems we have from 0 to pi for the vertical, and that's that. So I still want to think a little bit more why that's 2 pi r, 2 pi r r. See? So really, this is the length and this is the height. Seems to me that 2 pi little r should be enough, but I need to get little r at a certain r because the little r here will be different from the little r, let's say here. The little r going across is different, even though the radius is still the same. It's pretty odd. So the radius to the origin is the same length, but the radius across to the z-axis is different. You see how it gets shorter the higher we go up. So eventually, when we get to the horizontal, the two lengths are the same. But we have to account for the fact that this little r is a r at that certain radius. It still seems odd that we multiply them together, but we'll have to think about it more in the future to see why. So this is the length, 2 pi r at that circle times r, because that the little r at a particular height, and then height is the little bit of a width up and down that gets that surface area when you multiply all that together. And this is the integral, the final integral that they have to integrate to get the potential at that point using the potential formula. Uh, Another thing is that little r, this radius, let me delete some of these. Little r is r sine theta. So we'll also put this line here in terms of everything else, this horizontal line. That's the same thing as r sine theta, since this is my r coming out, this is the theta right there, which is opposite. So r sine theta is a projection onto that. So rewrite this integral again to the next page. Look, I'll have to rewrite this integral using that fact that we have r sine theta there. This will be the integral from 0 to pi of sigma in the front of sigma 2 pi r squared sine theta d theta over square root of z minus r cosine theta squared plus r squared. Everything in terms of r and theta, big R and theta, except for this little r squared. But I think that will be, oh, and I have to replace that one as well. Forgot about this one. Every single r, I'll replace. Single little r, this is going to be plus r sine theta squared. Let's make things interesting. So we have k 0 to pi sigma 2 pi big R squared sine theta d theta divided by the square root of z squared, and then we have minus 2 rd cosine theta plus r squared squared theta plus cosine squared theta. So that should equal k 0 pi sigma 2 pi big R squared sine theta d theta over the square root of z squared minus 2r z cosine theta plus r squared. Only taking an integral over theta, which does complicate things a bit since we have, and actually let me change this, since we have this in the denominator. So do is take an integral of the bottom one, will be sigma 2 pi big R squared sine theta. And we have this to the next line. Z squared minus 2rz cosine theta plus r squared go to the 1/2. I gotta multiply that by 2 and then divide by uh, negative 2rz sine theta, and some of these should cancel. I believe I will get negative k sigma 4 r z squared minus 2rz cosine theta plus r squared to the 1/2 over z. Uh, it's going to be evaluated from pi to 0. So it would be negative k sigma 4 pi big R over z. And then we have So the first pi will make that negative. So we have z squared plus 2rz plus r squared square root. And that'll make this one 1, z squared minus 2rz plus r squared to the 1/2. A whole lot of simplification in place here. If I could do some identities and stuff after this. I think I'll stop here with this one. Look at this one in more detail later. I do remember seeing this in discussion and seeing the uh, being clear on the different changes that they made. But let me ask about this one about the different identities or whatever they use to simplify the integrals and such. Let's see if this next one is a bit more straightforward. Imagine a spherically symmetric torus density. CR for R less than or equal to A, and 0 for R is greater than A. Determine the electric field and potential. Notice that VR and EX are continuous at R equals A. We have the torus density X equals CR, R less than or equal to A, and 0 for R greater than A. And to get the electric field, we'll do what we did before. The flux equals the integral of the electric field dA equals charge enclosed over epsilon naught, Gauss's law. And charge enclosed becomes a bit different. E dA cosine theta equals spherically symmetric charge density. So this will be E epsilon naught, assuming that's a solid uh, charge. Looks like they're doing the surface of a like not a volume with the surface. So I did before. as I go into more detail than the solutions do. Like sort of skipping this entire step and saying, let me draw this. Spherically symmetric force density. Um, CR, which means it's zero in the center, and as we get away from the center, it gets stronger and stronger, so it's stronger at the surface. And we know from earlier, I believe, if you have a surface density with an electric field, one of them is going to be sigma over 2 epsilon naught. So basically, very close to the surface, that'll be the E on both sides. Like if we zoom in and imagine like we're just very close to this wall right here. And E is also negative, the derivative of the potential. So taking these two together, like V, which is say minus VRO integral E dot dl equals C a to the fourth epsilon naught R squared for R greater than A and CR squared over 4 epsilon naught R hat for C less than A. Let's think about this. I'll recreate kin, the solution. So that would have to also equal the, have to equal this. So the charge enclosed would be uh, density volume. So if I make a Gaussian surface, let's see here, and I call this R, this should be E 4 pi R squared for the surface area, and that should equal E pi, and I believe we call the radius A, 4 pi A squared, epsilon naught. So these should cancel. One of these should cancel, it seems. So E will be C A squared over R epsilon naught. Have something slightly different. So I have to think about this one. Sometimes the solutions skip a whole lot of steps, which I hate. I'll see if I added something else. Okay. Okay. See what I forgot. So the charge density over here, I should have to integrate to get the charge because the charge changes. I was thinking about a continuous charge, but the charge is 0 here in the center. And because the charge density is CR, it increases as it goes out. So the charge at each outward ring is stronger than the inner ring. So the charge is not uniform. So we can't just take the volume. We have to actually integrate to get the actual charge. So it'll be integral E dA cosine theta equals CR, 4 pi R squared over epsilon naught. But I have to integrate dr. So that's the difference in this one. And actually I can efficient. I'll just make an extra line. So this will basically be, this will be E dA R squared. Excuse me, E 4 pi R squared, since that's the area. And we're just saying that this R is just whatever random R. We're going to assume that uh, we go within. We'll just say this R is less than big R. We'll just say the Gaussian surface is here. So that means that the R for the charge and the R for the uh, Gaussian surface will be the same. So I guess that's 4 pi R squared. The angle will still be 0 since normal is still perpendicular at every single point. And now we have the integral of that with r ends up being r cubed, so that ends up being c r 4 over 4, 4 over epsilon naught, and that's going to be the integral from 0 to r. It's going to be e 4 pi r squared equals c r 4 pi over epsilon naught. And now we could cancel these two. So this will be e equals, to cancel this as well. E equals CR over epsilon naught. This is still squared. And it says for R is less than, say, A within the surface. And this will be in the direction going outward. That's the electric field, the radial electric field. All right. So that's a detail that I missed. So basically we entering our way back to here. Okay, so that matches. And I was looking at the wrong one earlier, by the way. Just noticed that. So normally I'll put it in this order here. So you notice I did the inside the sphere first. That's the order I usually go. But still, it caused me to look at it more closely and see what was going on. Mm. Now we have the electric field inside. This is R. Now we'll do the same thing for outside. So now the Gaussian surface is at the green mark. This would be our R now. I'll just call it R1, so I should just call that one R. So we have E, the flux equals the integral E dot dA, and that still equals the charge enclosed over epsilon naught, and charge enclosed equals sigma dA, because each area is a different charge. We have to add all of those up to get the volume. So it would be E dot dA equals CR 4 pi r squared CR over epsilon naught. And this time we're integrating from 0 to R1. And this time the different ones would be different. Actually, this one is integrating from 0 to R1. This one is going from A. So the charge stops at A over there. The charge goes all the way up here. I can actually go ahead and do the dot product there. We have this. So we have E uh, 4 pi r 1 squared equals C 4 pi r 4 over 4 epsilon naught, going from 0 to A. So this is E 4 pi r1 squared equals C 4 pi a to the fourth over epsilon naught. So now those are different. So I can still cancel the pi's. Now we have E equals C a to the fourth over 4r1 squared epsilon naught. And looks like that matches as well. We got that worked out. So that's how we got the electric field, having to remember to integrate the charge density on the right since the charge is not symmetrical. Like the charge gets stronger from the center, going from 0 to the maximum CR at A. We have to integrate to get the actual charge that's within that volume. I still think it's interesting that we integrate. That makes sense because I was about to say, talking about the integration here, but since this is a volume, we have the area here, and I'm adding up all these different surface areas. I have one sphere here, plus one sphere there, plus one sphere there. When I add up all the spheres, I get a volume. So it's basically a volume equals length times width times height, and the length and the width is going to be the density at the surface, and the height is going to be the radius. So this becomes integral times r, and I'm adding up all the r. So this will basically be integral times dr. So I'm adding up all the r, and that's a surface area. So okay, that's nice. Uh, we have the electric field, and I think I wrote somewhere here that the potential. So I take the integral of the electric field, I get the potential. So E equals negative dV over dr plus V equals integral negative E. I guess that'll also be dr. Yeah. I shall do this integral real fast and probably take a break. Oh, let's see. Yeah. Let's take a look and see if I don't, before I miss something. So we're using the method of, so we have a charge and electric potential at infinity would be 0. And here the electric potential will be a certain point. So I can add up the electric potential from there to there. Or I can add up the electric potential from infinity to there. Just depending on how we add it, the difference will be the same. I guess just to say the potential at that point is is what it's going to be. Choose this here, the difference is 0. If I choose this point, the difference is that. Choose this point, it's at the surface. So I'll have to think more about the details of that. One of the classes I helped with, the professor went into detail about um, the normalization of integrating from infinity. So we can say the integral I'll take. So it looks like the way it's being done. I'm going to take the integral from infinity to here, and I'll take the integral from infinity to here. and then I'll get the difference of those two and get the potential there. Makes sense. That basically simplifies the calculation. So let's do the first one. So V equals negative integral E VR, and that equals negative integral infinity to R. Um, Basically, this is R here outside. This one here, that works. Called it R1 before. So we'll say this is R1. And we'll say A is the size of the charge density from infinity to R1 of the electric field at R1. That's going to be go to that. And then roll the dr. So that'll be that's going to equal negative CA to the fourth over 4R1 epsilon naught and positive, and from R1 to infinity, that's going to be CA to the fourth over 4R1 epsilon naught, and then infinity one will equal 0. Let's see if I got that right. That seems okay. Yeah, R1. And then we'll say V at A is negative integral electric field at ADR. So going from infinity to A. That's going to be from negative infinity to A. I'll just copy down the A one. If anybody else have a question, be sure to drop a line. I'll close up shortly, so let me know if you have a question on anything we did so far. Um, I didn't miss anything with this one. Okay, so far, one. Must be some trick with this one because this one, the integral will definitely be add up to infinity. I see I scratched that out on my notes. Let me see what other thing there may be. So for r less than a, it is c r squared forward on that. The integral to a, second integral out, like it's going from a to r for this one instead of from infinity to r. A, infinity to a to r. Going from infinity to a, which is the bounds, and R is in the inside here. We're going from infinity to A, then from A to R, and getting the difference between those. So, right, try this. Infinity to A, we're using the uh, uh, less than formula for one and the greater than formula for the other one. So for infinity to A will be the same formula here. Boom. I'm just going to stop it at A. Because I have to use the outer formula because that's the formula that gives us the potential outside. And integral of, which I believe should technically be plus, we have, that's why they made it minus because they switched the bounds. So we could do the same thing, switch the bounds and make it go from A to R. And now we have to use the inner electric field, which would be this one. And also integrating from D, right? So let's see what we get. Actually, this would be the same. Just we're plugging in R, so this should be this. Saying we're plugging in A, I meant to say. So it should be this, and things to sign on that one. Let's actually do this integral here. This would be CR3 over 12 epsilon naught from R to A. So this should be C A to the fourth, A to the third over naught minus CR to the third over 12 epsilon naught plus CA to the third 12 epsilon naught. It looks like there's a simplification in the solutions that I'm not seeing. Let's see. At a potential is 0. So at the surface, there's a discontinuity. So it ends up being C A cubed epsilon naught minus CR cubed over 12 at the boundary. One difference, I see that they have a 3 here instead of a 4. They're not sharing how they got. Hope you all found it interesting. Thank you for joining, Sergio. I'll probably be later to do either finish these problems or do some quantum problems. Looks like I just did part A of this one so far. So maybe I'll come back later and finish B or switch to some quantum. That way I go out, I'll finish doing all these problems, reviewing them. And hopefully I'll see y'all next time. Y'all be cool. Thanks for joining.